let me kind of put things into perspective a little bit here. We started by looking at grid electrostatic potential calculation of grids, and then matrix multiplication. And for these kind of things, the access pattern, okay, the access pattern for the data is predetermined. Okay, so when you say, okay, here's matrix multiplication, matrix M, matrix N, you know that the access patterns.
Did you put mic?
What's that?
Did you put mic?
Yeah.
Okay.
Yeah. So can you hear?
Yeah.
Wait, then why did you ask?
I was skeptical. I did not see the mic.
Oh, but can you hear me in the back? Okay.
I can hear you.
Okay, good. So, so the matrix multiplication is such that you know, in order to produce an output output element, a row of M and a column of N is involved, right? So these are the things that you don't even need to look at the data value, and you can tell, and then you can design your data access patterns. The atoms in the electrostatic potential calculation was one kind of step away from this. Which grid requires that atom in the cutoff kind of algorithm depends on the coordinate of the atom. So that's why we do the spatial sorting. But at least the data value that you can pre-sort the data according to the data value, right? So we can do a pass through the atom, and we can do the uniform binning, right? We can do the compact binning, right? So all these things can be done before we start the calculation. Okay. So this is a little bit less, static, but at least before we do the calculation, we can just look at the data value and do some arrangement, and then life is good after that, right? So today we're going to look at graph search, and we're going to start to look at some of these, the computation, where we're going to have potentially a very, very large data structure. And if we look at the data structure, we still have no idea how the access pattern is going to be. And it's going to depend on where we're going to start the search and how the search propagates through the graph. And cycle, iteration by iteration, we're going to discover more and more and more of the data that we're going to process with fewer and fewer. So even if we scan through the entire graph at the beginning, we still don't know how the beta pattern, access pattern is going to be. So this is going into the dynamic data, what we call the dynamic extraction. Okay, we go into a big data structure. Every step of the way, we're going to identify a subset of the data that should be processed. Okay, and then we identify the next subset. So these kind of dynamic extraction is incredibly difficult, and oftentimes they impose so much stress on the memory system that these things can be extremely, extremely slow. And this is the reason why, even today, DARPA and so on still have these challenges, the big graph challenges and so on, because the computation of these things are so much a mismatch with our current computing system, right? How we organize our memory system, that it's really, really hard for for the existing systems to get efficiency, parallelism, performance. So we're going to start with the simplest form of this. Okay, so the breadth first search. Breadth first search in a graph is what I call the entry-level computation for graph. Okay, and it is really the simplest form of the graph computation, but it already start to to give you some good insight into how we should be addressing these kind of irregular dynamic behavior. And in this kind of search, we're going to be introducing queues, and these queues are not that different from some of the queues that you have learned before, but these queues are going to need to have extremely high bandwidth, high throughput, because many data elements need to come into the queue, and many data elements need to go out of the queue. so that you can keep that parallel computation going. So that queue structure needs to have extremely high throughput, and the only way that we can get that kind of high throughput is actually the privatization technique. So this is a prime example of how when we replicate data structure, when we privatize data structure, we can get much better parallelism. But then, exactly because of privatization, we also have some very limited scope in terms of the problems that we can solve with these kind of things. Some of the problems cannot be solved with privatization. I'm going to go into a couple of the details. So the objective here is to learn the role of privatization in the scalability of algorithms that are not amenable to scatter-together transformation. And so it's for dynamic input data extraction or histograms, lightweight scatter. So we already talked a little bit about this in 408 in terms of histogram, right? So that was an easy privatization. You were trying to accumulate the frequency of each type of the value, right? The buckets of values. So now you create multiple versions of the histogram and have all the threads to increment these histograms, in their private versions, and then eventually you combine them. And the reason why you can do that, remember, is because the histogram calculation is associative and commutative, right? So it doesn't matter which order you accumulate value. So that's why you can accumulate them into these separate histograms, even though the order in which they will be added into the final histogram will be very different than if you have a sequential process that accumulate only into one histogram. But because of the commutative and associative nature of the computation, you can do that, right? So that was the 408. So here, it's a little bit more sophisticated, but fundamentally, you should realize that at some point that it's actually not that different. So we want to learn the efficient queue structures that support massively parallel extraction of input data from bulk data structures like graphs, and to learn efficient kernel structures that cope with the dynamic variations of the working set size. One of the consequences of this dynamic data extraction kind of computation is that the amount of work that you're going to see will vary in time. Okay, so you're dynamically extracting data to process, and depending on the nature of the computation and your steps, your amount of work that you have in each iteration may grow, shrink, and they can actually vary dramatically. So that's why sometimes we need to actually organize our parallel execution differently according to where you are. Are you in a less parallel phase or in a more parallel phase? So this also begin to get into the point where we start to need to have different organization or arrangement of your code in order to be able to handle this dynamic variation of data, the data that you need to process. Okay. So this is why we reserve these kind of computation for graduate level classes. So for undergraduate classes, we typically will teach these more static nature and the things that you can sort of more have simpler exam questions, and then the more kind of cleaner code that you can write, and then as you get into grad school, you start to get more and more into the real world. Okay, now you're beginning to see more ugly things and more the third year side of the business, right? So this is where we start to see more laundries and 30 club. So let's go back and kind of review this a little bit. We actually kind of keep going back to this several times, right? We first talk about the scatter to gather, and then when we talk about the spatial sorting or binning, we came back and we'll talk about scatter to gather, right? So here, the reason why we talk about that is because we're going to need to be able to we can no longer easily collect these data very easily, we need to use the data value themselves to determine whether they should be gathered by each thread. So that's why we led to the spatial sorting part. But here, we have something similar here. So in many applications, the inputs are not easily identified, upfront. So for the binning applications, at least when we look at the data, we say, okay, so these are the input that will be used by certain threads. But in the graph type of computation, the threads are not going to be able to, we're now able to determine upfront what each thread should be processing. So this makes the scattered together calculation a lot more difficult. So that's why we're going to be using these dynamic data extraction kind of techniques. So the data to be processed in each phase of the computation need to be dynamically determined and extracted from a bulk data structure. So this is harder when the bulk data structure is not organized for massively parallel access, such as graphs. So when you have a simple two-dimensional array, given two indices, you'll be able to easily just find the element, right? So if many threads need to access those elements, as long as they have the indices, they can just go in and easily find the position and fetch the data, right? So this was actually what binning is about, right? We can translate very easily from the spatial coordinate of the grid points and into the bins that contain all the atoms, right? That are relevant to the calculation of those grid points. However, in graphs, it's actually not that easy. We'll need to follow these edges and to be able to find the next group of people, nodes that we need to use in order to do the computation. So the graph algorithms are popular examples that to deal with these dynamic data. It's widely used in electronic design automation and large-scale optimization applications. So we use, as I said, the simplest form, breadth-first search, as an example. So what's the challenge in dynamic data? The input data needs to be organized for locality, right? As we saw before, in matrix multiplication, we organize, right? We organize data for for locality, for coalescing, and for contention avoidance, as we access them, right? So we said that remember for the joint, out of the joint tiling, we transpose one of the matrices, right? These are the kind of things that we do to make accessing these data more efficient in our memory system. Basically, we can use the DRAM burst, much more efficiently when the accesses are coalesced. And now, the amount of work and the level of parallelism often grow and shrink during the execution. So as more or less data is extracted during each phase, so it's hard to efficiently fit into one CUDA kernel configuration, and this cannot be changed once it's launched. So different kernel strategies will fit in different data sizes. So these are the two things that we're going to address for the rest of the class today, and probably some portion of Thursday. Okay. So let's first talk about graphs. So this is a very, very simple graph, and this is a directed graph. So all the edges have directions, and so we can have a pointer form of the graph representation, and then so we can say, okay, here are the nodes, and then we can just have a pointer from let's say node 7 to node 0, node 0 to node 2. So we can just have these edges, right, represented as pointers. So theoretically, we can just represent a graph as structure of let's say nodes, and then each node will have several edges, right, coming out, and then point to the, to the next node. But these are, reasonable, intuitive representations in classes like, 225. Okay, but they're not for serious computation. The overhead for representing those kind of the graphs is too big. So in order for to represent something like this, you need to have a node, and then you need to have some kind of a list of pointers, and then you need, so each one is a full address pointer, and then when you need to go from one to the other, you need to do a full memory access, and then you need to go into the right field, and then get to the others. So you have dynamically allocated number of pointers for each node, because you have variable number of edges, right, coming out of each node. And then if you need to do the other direction, you need, if you want to find which one can come to you, right, then you're out of luck, right? So you will need to, you need to have a reversible representation of some sort to say, okay, these are all the nodes that can come to me, right? And then you need to allocate even more of those pointers, and those pointers would hopefully give you the information. By the time everything's said and done, you will have probably, for each node in this, sort of each typical size graph, you will probably have, an order of magnitude more memory locations you need to allocate in order to keep all that information for you to be able to traverse that graph. Okay, so even though it's very intuitive, it's not the best thing to do when you try to handle a very large scale graph in reality. So people know this problem, and people have been studying these kind of problems for a long time. So basically, there is a direct isomorphism between a pointer-based graph representation and a matrix-based graph representation. So this is what we call the connectivity matrix. So basically, when you have a directed graph, you will go from the nodes on this side to the nodes on this side. So all the nodes are listed on the row side, and all the nodes are also listed on the column side. So whenever you have an edge from one of the nodes to another node, let's say from node 6 to node 8, then you will start with 6, and then you will go to 8. So there will be 1 here that says there is an edge. So you also have weighted versus non-weighted graph. So in this particular graph, all the edges are of the same value. So there's no difference in terms of the weight of these edges. But if there is a weight, for example, this may represent distance, right? These may be cities, and this may be how the distance between the cities. In that case, there is a value here, and then so this is no longer 1. This is going to be that distance, right? So this is actually a very typical representation in your GPS. Okay, so in the GPS, you represent all these different places when they do the routing. This is a very important data structure. One of the important facts of this is that invariably we're going to have sparsity in these matrices, unless you have a fully connected graph, right? Unless you have a fully connected graph here, you will have a lot of empty, right? You'll have a lot of 0 elements in this matrix. Okay, so that's why very few people will represent a large graph as a full matrix. We will represent this as a sparse matrix. So that's part of the reason why we teach sparse matrix computation in 408. And sparse matrix is not just about representing your typical numerical matrices in a more efficient form. It's because whenever we represent these graph data structures and many of these other types of graph is probably the most dominating part into matrix form, we will invariably have sparse matrices. So that's why there is a direct isomorphism between sparse matrix computation and graph computation. They're almost always, directly transferable in terms of the techniques that we have in each domain. So here, by having these ones, okay, in the connectivity matrix, then we can exactly recover all the edges, right? So the question is, how do we represent something like this efficiently? So if we only want to be able to go from one node to another node through a directed edge, then all we have to do is to represent, for all the nodes, the places that you can go from this node to the next, right? So this brings us to the compressed edge representation of a graph. Okay. So the way to think about this is that we're going to have, essentially a list of all the edges, all the edges that can come out of a particular node. So we're going to start by compressing everything into a CSR column, compressed representation in the sparse matrix that we went over in 408. So basically, the way to think about it is that we're going to take a row view. Okay, we're going to take a row view. So each row is going to have a section, a small section in the array that we use to represent as graph. So this is given by the row pointers. Okay, so these are so this array gives us the beginning location of all the edges, for that particular source node, okay, in the graph. So because node 0 has 2 edges out of it, you would expect the next node, node 1, will start at location 2 because 0 and 1 will be used to represent those 2 edges. So these two are in the column index. It said you'll give us the destination. Why? Because the column index is exactly the node index. So if you save the column index for these 2 entries, that tells you the destination node number for the edge. Make sense? For the edges. So here, I'm saying I see a 0, so I know that all the edges coming out of node 0 will start with location 0 of the column index array. And then the next one starts at 2, so I know that these 2 belong to node 0. And I know that this one goes to node 1, and this one goes to node 2. Right? Okay. Now, the next one, node 1 also has 2 of these edges. One goes to 3 and one goes to 4. So that's why, when I look at this, I know that it starts with location 2, and the next one starts at location 4. So 2 and 3 will give me, in this column index matrix, will give me the node numbers, right? The destination node numbers for that node. So it's 3 and 4, indeed. So node 2 can go, node 1 can go into either 3 or 4, right? So if I continue to do this, I will exhaust all the nodes, right? All the source nodes. And then here, I will have all the edges with all the destination numbers, right? All the destination node numbers in this array. And I can use this to store the matrix value. But in this case, it's all ones. If it's all ones, I can just ignore it, right? I can just not store. If everything is 1, why do I need to store it? However, if it's weighted, then I will need to store it, right? So that's kind of the basic format. So this is a compressed sparse row representation, CSR, And this is a very convenient representation when you only need to go from a source node to a destination node in your computation. If you ever need to reverse, going back from a destination to a source, you're in trouble with this representation. Make sense? Right? So then you need to have something else. So this is what I call the entry-level poor spans approach to representing graph. And each representation from this point on will have additional cost and give you additional efficiency, but then the trade-off is going to be that you may need to store more, you may need to access more data, in order to be able to get that computational efficiency, which may or may not be always a good thing, because in many of the modern computing systems, the memory access latency can actually outweigh the computational efficiency. So these are the kind of things that make the graph computation extremely hard. Okay? Any questions? This is very, very important. You need to really understand when you read something like this, you're reading a graph, and you can quickly know how to find how to find the section of the edges for each node, right? And then this gives you the efficient computation, on the fly. So let's take a look at the breadth first search algorithm. So the definition of breadth first search is that you want to determine the minimum number of hops that is required to go from a source node to a destination node, or all destinations. Okay. So basically, if you are given a graph, and someone has to tell you where you're going to start. It can be any node. Okay, so breadth first search, if anyone tells you a source node, let's say 0 for the sake of argument here. Let's say if we start with 0, then we start with that source node, and we need to identify and mark all the nodes that can be reached from the source node with 1 hop, 2 hops, 3 hops, right? So these, we will need to start with this node and say, okay, with 1 hop, what are the nodes that I can get to? Obviously, it's going to be 1 and 2, right? That's easy. And then you say 2 hops. 2 hops will be 1 hop from those nodes that you can reach with 1 hop, right? So then you go from here and say, okay, these are the 2 that I can go with 1 hop, and then these are, these are the 3 that I can go with 1 hop from this one. Occasionally, you will see a node that you have already visited before, and that means that that node can be reached with fewer hops, and you shouldn't include that in the current calculation, right? So that's simple, a very, very simple definition of breadth first search, right? Okay? So what we would like to do is, I'd like to have both of these marked as 1 hop, and then these as 2 hops, right? All these as 2 hops. And then eventually this is 3 hop, right? So if I have a different source, I could have a different source like 2. So if I start with 2, then those that can be reached in 1 hop will be this one, and this one, all the immediate neighbors, right? And then the 2 will be this one, right? And this one. So you go from 7 to 0, and from 6 to 8. So as you can see, even though I'm only changing, making a very small change in terms of where the source is, the outcome can be dramatically different for the nodes. This is the reason why it's not easy to reuse the calculation of breadth first search. And oftentimes, if the algorithm, if you can have a simple algorithm that can reuse most of the data from the neighbor, a lot of times you can amortize costs and so on. But here, because the slight change in the source position can affect the output in a very dramatic way. It's hard to use kind of amortization and so on to reduce the cost of the calculation. So, how do we typically do a breadth first search algorithm? Typically, we will do exactly what we said. We will create these frontiers. Okay. We start with the source and say, okay, which are the nodes that I can reach in one hop, right? My immediate neighbors. So let me grab all the immediate neighbors. So I grab 5, 6, 7. So this is what I call the frontier. Okay. So these immediate neighbors are the frontier. So this is exactly how the law enforcement figure out how to arrest all the people in a gang. Okay? They go on the street, they arrest some of the gang members, and then they interrogate them a little bit, and then they found their immediate next ones, and then they go on the street, arrest the rest of those immediate next the gang members. They investigate them a little bit, and then they found that they're immediate friends, and then they investigate more, right? So this is widely used technique in all kinds of fields. Second frontier. So now once you have the frontier, you start to create the next frontier, right? You arrested all these immediate friends, and then you go and you arrest their immediate friends, right? So that's exactly how the frontiers work. So you will from one frontier you do the next immediate next ones, and you create the next frontier, and eventually you will exhaust all the possibilities, and that's when you know that the entire gang will end up in jail, right? So this is when you stop, and you probably start to see some pattern. That is, at the beginning you may have only one source, so you need to kind of ramp up your frontier, right? But the source node may only have a few neighbors, and then each of the neighbors can give you several neighbors. So you will have a growing frontier at the beginning. And then in the end, you may have a shrinking frontier because you have exhausted most of the possibilities. So then each additional frontier only will pick up a few more until you finish with the entire the graph. Make sense? So you should envision some kind of ramping of the size of the frontier and then come down, right? In the end. So again, slightly different, the source will give you very different values, right? For these, for the results. So let's say, how do we, process frontiers? So this is, we start with two. We're going to have the first frontier of 5, 6, and 7. 5, 6, and 7. So and then 5, 6, and 7 each will lead us to, so we'll look at the immediate, the destinations for 5. It doesn't go anywhere. It only goes to 6, but 6 is already processed. Remember that? So once it's already processed, it doesn't make sense to process it anymore. However, 7 will give you 0, and 6 will give you 8. So 0 and 8 will be your second frontier. Right? So this is what we're doing a snapshot here. So we have 0 and 8 connected here. So this is the interrogation room now. Okay? So we're interrogating 0 and 8. So who's your friend? Who did you go to lunch with? And and then they'll say, okay. So then you go to 0. Remember, how do we get to the neighbors of 0? 0 tells us to go to the row index pointer 0. And then it will give us the beginning location of the edges. And then 1 in that row pointer array, it will give me the beginning of the next one. So I know that these two, right? These two are the edges. So these are the row pointer array value 0. So I go to 0, and then the next one is 2. So I know that 1 and 2 are the two edges. So I know that 1 and 2 will go to a array where I'm going to be labeling all these nodes. So I'm going to have from node 0 to node 8, and every one will have a label. I will start with -1 when I begin the process. As soon as I realize the first one hop nodes, I will mark them as 1. So that's why I have 1, 1, 1 there. And then I'll mark the next one, 0 and 8, as 2. Now I'm discovering more, right? When I discover more, I will follow this one and say, okay, so for 0, I'm going to have 1 and 2. And I go there, I realize that only 1 has a -1. That means that it has not been visited. So I will go ahead and label that as 3, right? But the other one has been visited. It has a 0 value in there. It's the source. So I'm not going to further process that. So as far as the 0 is concerned, the only next frontier node that I'm going to have is the 1, right? Node 1 there. And 8, same thing. I go through the edge array. So that, I go to row pointer, and it says 15 and 15. So that means that the last one, when I see this, say, there's nothing here, because it starts with 15, and the next one starts with 15, so it's empty list. So I don't have any edges to work with. So the only one that I'm going to be able to pick up for the next frontier, in this case, is 1. Right? So this is how I'm going to go from one iteration to the next iteration. I take the current frontier, I follow through this row pointer array, access all the destinations, and check whether they have been accessed or not before, visited before, and then I'll mark them, the unvisited one with the current hops, and then I also put that into the next frontier, right? So this is the reason why we call this dynamic data extraction, because in every iteration, we're going to take a few of the data, put them into a frontier data structure, and this is the input. This is the input to the next iteration, right? And then we'll go from there and process through the data structure. Right? Clear? Yes.
So isn't it possible to choose a starting node such that you don't actually get a chance to have your frontier ever contain certain nodes?
Yes.
They started with 5 or something.
Yes, yeah. So that would be correct, because in some cases, some of the nodes may not be reachable from a source. So when you have any node that remain as -1 after you're done, after you can no longer find any more frontiers, that means that any -1s means that you cannot reach those nodes from the source. Absolutely. Yes.
This is like a lot of cost for synchronization, and it's like mutex lots on this like this.
Possibly. And that's exactly what we're going to get into, right? But I want to make sure that at least we understand, the kind of the basic of the algorithms, right? So this is actually used extensively in things like routing in large UIUC chips. So basically, in these chips, when you route, you're going to place wires on the chip. So these are the existing wires that you already placed on the chip. And then you say, okay, the next one requires me to route from this pin of it. So then there may be a logic here, and then you have a pin for the logic, and you need to have another block of logic, and you have a pin here. You need to connect these two logic, right? This is a very typical kind of routing, even for FPGAs. In FPGA, you can think about this as a lookup table, another lookup table, and then you're connecting all these the pins from the lookup table to form the logic. Okay. So what you do from from this one is you find the immediate next ones, and then you find the immediate next one. At some point, you'll start to hit these these edges. So when you have an edge, that means that the node is no longer available for you. Okay. So you would just keep doing this until you have big enough frontier, and then eventually you will wrap around and get here, and then you hit the destination. So once you hit the destination, you finish the breadth first search. So in this case, you don't have to exhaust the entire graph. Your ending condition is when your destination is among the frontier that you just discovered. And the number of hops in that frontier will be what?
Short distance.
The number of the squares that you go through, right? And then how do you find that path? You just follow the 1, 2, 3, 4, or you go back. You go from here, find the one fewer, and one fewer, then eventually you will just reach the source. You may have multiple ways, by the way. So there's some heuristic involved if you have multiple ways to choose. For example, you may want to have a straighter line connection, as straight as possible rather than zigzagging, right? So there's certain heuristic involved when you have some choices. Make sense? Okay. So that's the usage case. So when we have these kind of graphs, so let's say here's a kind of a little graph. S go to R, R go to B, S go to W, and so this is the kind of the little thing. What we end up doing is we start with S, and then we generate the next frontier, which is the R and W. And then we generate the next frontier, which is the B, T, and X. And then we generate the next frontier, which is U, Y. So if you just list all the frontiers that you have, you will have level 1 frontier, level 2 frontier, level 3 frontier, so on. So you're generating essentially a tree, right? Generating a tree out of that graph. So sometimes people will call this spanning tree and so on, that the graph computation, right? Okay. So let's first talk about a efficient sequential algorithm. From sequential algorithm point of view, people oftentimes try to minimize the number of computation steps, right? For sequential, reduce the computation complexity. A efficient sequential breadth first search algorithm should be of the order of number of vertex or number of nodes plus number of edges. So it's a linear algorithm. It's linearly proportional. The complexity is linearly proportional to the size of the graph. Okay. If you have a lot more edges than the nodes, then it's proportional to number of edges. If you have a lot more nodes than edges, because it's an extremely sparse graph, then it would be proportional to the number of nodes. Okay. So the way that we do this is in the sequential algorithm is we maintain a queue. Okay, we maintain a queue, and this queue is going to receive the frontiers. So we start with the source. So we put the source in here. So this is the first frontier, trivial. The trivial first frontier, which is the source. And then we process the source, and we discover the next frontier. We put those into the frontier. So now we have the hop 1, right? We have the hop 1 nodes. And we process these two hop 1 nodes to identify the VTW. These are the hop 2 frontier. So we exhausted that frontier, produce the next frontier, hop 2 frontier, And then we exhaust all these, process, and generate the next frontier, and these are the four frontier. And at that point, we have completed all the computation. So you can show that you will only visit all the nodes. You're not going to visit the nodes only once, because sometimes you need to, to follow some edges, right? You need to follow some edges. So, but you will never process a node more than the edge number of times, right? So that's why the complexity, you can show that the complexity of the algorithm is bounded by the number of nodes plus the number of edges. Okay, and that's kind of a typical proof that we asked you to do in 374 kind of situation. Right? There's a good reason why we asked you to do those kind of proofs. Any question about the sequential algorithm? The brutal part about this kind of search is that the sequential algorithm is a linear algorithm. It's extremely efficient. It's lean and mean. Okay? So that's why it's very, very hard to beat a sequential algorithm with parallel algorithm. If your parallel algorithm had higher computational complexity, remember, this is the reason why I bothered to show that quadratic and Lagrangian curve, right? You may blow up the resource requirements so much, the execution resource requirements so much, that you don't have enough execution resources to be able to swallow the additional computational complexity, and you will end up with slowdown. Okay? So one of the popular ways to do parallel breadth search is by doing parallel propagation in each level. That is, once you have a level of frontier nodes, you have the threads, each thread to process one or a small number of these frontier nodes and generate the next frontier, right? So I can have two threads here to process in parallel to generate these frontiers, and then I can have three threads here to generate the next frontier. There are two problems involved in this kind of approach. One is the threads. The threads need to have a good way to take the subset, right? The threads have to be, each thread has to have an easy way to identify the subset of nodes in the frontier to process, which actually is reasonably easy. And then they need to have an orderly way to insert the new frontier nodes into the queue, right? And that is an atomic operation. But we need to assemble a good representation, array representation of the frontier from the computation result of the previous frontier. These parallel threads need to be able to place these things into the appropriate locations, so that you have a nice, neat, continuous list of frontier nodes for the threads to come in and grab subsets. Okay? So you don't want to create a whole lot of holes in your array and so on. That the next iteration may not be able to have efficient computation, because if you create those holes in your array, the next threads need to come in and check and see if it's a hole or not, and that already blow up the computational complexity. Okay, so that's the difficult part. And the other difficult part is that the threads are not associated with a data all the way through. Each iteration, the threads need to come in and negotiate about which node to pick. So when you have a large number of nodes versus a small number of nodes, there is a synchronization going on here. You don't want any of the threads to start to process the next frontier until you know you have already finished this frontier, because you don't want to mislabel the nodes. If you start the processing of the next frontier too early, you may mislabel the nodes, right? So you need to make sure that you have already finished with all the level 1 nodes before you process the level 2 nodes. And there is a barrier synchronization involved for that correctness. And that barrier synchronization can be less expensive when you have fewer data elements with fewer threads, and very, very expensive when you have a large number of threads involved, right? So how do you handle that synchronization cost is one of the, I would say, common challenges for this kind of computation. So the easy way to do this is actually by launching kernels at each step of the way. So let's say we start with source, and the source, so when we only have one node, so only one thread will be handling that source, and that thread will generate R and W into the array. And then we launch a kernel. We launch a kernel on this one, and with 2 threads. Each one will produce 1 and 2, right? So this kernel will generate these, the next level, and then the kernel ends. And you launch another kernel, and then you process these 3, and it will be 3 threads. And each thread will process one of these and generate the next level. So this gives you the automatic barrier synchronization, because these things will be in the global memory. When the threads write into the global memory, the only way to really have a good, clean barrier synchronization and memory consistency is by ending that kernel, launching another kernel, so that the threads now will have a clean global memory that they can fetch the nodes from. So that's why you have this kernel launch and kernel launch and. So when you write a piece of code, a very basic breadth first search GPU code is going to be iteratively launching kernels, okay? And for each launch corresponds to one level of your frontier, right? Until you exhaust it, until you no longer find any more frontier, right? That's when you have finished with this breadth first, and whatever is not reachable at that point is not reachable. Okay, so you know when to end. Any questions?
Yeah, can we do like recursion with this kernel launches?
In fact, you could. So I'm going to come back to this because that's one of the actually the better higher performance implementation by using dynamic parallelism, recursive kernel. Very good. So wait, we already done this. Okay, so there are many breadth first search applications in all kinds of areas, and in VLSI CAD, informal verification of reachability analysis, clustering for finding connected components, logic simulation, timing, and logic synthesis. So all these things typically require breadth first search in the graph representation of the of your circuit. So now, there are some earlier attempts to parallelize BFS. So mathematicians and algorithm designers have been looking at these kind of problems for years. And there are typically 2 kinds of approaches. One is what we call the sparse matrix traversal kind of approach, and the other one is algebraic matrix multiplication or matrix vector multiplication kind of approach. So because there's a direct correspondence between graphs and matrices, right? We have the connectivity matrix. So we can formulate the traversal of graph with matrix vector multiplication. And this brings us into the algebraic domain. Sometimes it makes sense, sometimes it doesn't make sense. So let's kind of go into this a little bit more detail. And this is actually something that you will constantly run into in these kind of computation. It's very, when you go to a conference, people will immediately start to argue, okay, whether the sparse matrix, the iterative sparse matrix methods work, or you should do the matrix vector multiplication algebraic approach. And people are very passionate about it, by the way. there's certain people who will never talk to people who use the other approach. Okay, this is like really like politics. People can be very emotional. So so if you want to spoil a conference dinner conversation, go into this. Now, so we can do the node-oriented parallelization, and the threads are assigned to nodes, or we can do the edge-oriented adjacency matrix or connectivity matrix-based approach, parallelization, and we can parallelize the matrix multiplication for computing frontier propagation. So, this is something that it should be kind of remind you of something in ECE 408. So remember when we did the convolution layer, we formulated it into matrix multiplication, right? So here you will see the repeated kind of effort in formulating everything into matrix multiplication or matrix vector multiplication. This is one of the reasons why one of my dear friends in computer science always ask the question about matrix multiplication in qualifying exam. And this is a senior faculty member who has been around for a long time, and he passionately, very passionately claimed that if a student does not understand matrix multiplication, the student does not understand computer science. Okay, so part of this really a lot of truth to it, because so many types of computation can be formulated into matrix multiplication. So that's why I tend to agree with it. So the potential of the pitfall of parallel algorithms is this. If you are not careful, sometimes you can generate a very nicely formulated parallel algorithm, but then you have a increased computational complexity, and you start to have much higher level of number of operations. So let's start with the first one here. Here's a IIT breadth first search algorithm, and this is to accelerate large graph algorithms on the GPU using CUDA paper. And each thread is dedicated to one node. Okay. So each thread is dedicated to one node. So the thread, in every iteration, the thread wakes up and check if there's anything that needs to be done for that node. So it's going to look at all the edges for that node and determine whether there's something that needs to be done. So the number of threads is fixed at the number of nodes. Okay, and this, you should be a little bit alarmed at this point, because remember, in each iteration of that propagation, only a small subset of the nodes are involved in the frontier, right? So in a sequential algorithm, the computation and every iteration is extremely lean, right? It's only focused on the nodes in the frontier, and these nodes only appear in the frontier once. Right? So you really don't process and reprocess the node by going through these edges more than once in the sequential algorithm. Right? Okay. So now with this approach, you said I'm going to make it very parallel. Every iteration, I'm going to have all these threads wake up, and every thread is going to go to a node and look at the neighbors. Okay, of the node. So what are we looking for? We examine the neighbor nodes to determine if this node will be the frontier node of the next phase, right? So let's say I'm responsible for node K. Okay, node K, and I know that I'm currently at iteration. Let's say iteration 3. Okay, iteration 3. Then I wake up, I go and look at all the neighboring nodes that can come to me, right? That can come into me. By the way, that also should give you a little bit of alarm, because the representation so far that we have goes from a source node to destination node. in order for this algorithm to work, you need to have a way to go from a destination node to all the possible source nodes. So you need to have an inverse representation, right? So that CSR is not going to be sufficient. You need to have another source, inverse list, right? So, fine. And so you say, okay, I'm at iteration 3. So if my node is going to be the frontier, it's going to be iteration, it's going to be 4, right? 4 hop. So I'm going to go look at all my neighbors and see if anyone is 3. If anyone is 3, that means that I'm going to be 4, right? Right? As long as I have not been visited before. So then, if so, I put the node into the, I put a 4 into my node. And that's the action for putting the node into the frontier, right? So it went from -1 to 4 now. Next time when I wake up, I'm going to look at this, oh, -1,